During a routine observation in Algonquin Provincial Park in Canada, a researcher watched a red squirrel disappear into a snowdrift and return with a cone it had buried 3 months earlier, 3 feet beneath the ice. The squirrel went to the exact same spot, dug down through the snow, and retrieved its food within 20 seconds. This shouldn't be possible. Snow erases markers, scents vanish in frozen temperatures, and remembering hundreds of locations for months exceeds normal memory capacity, but red squirrels don't have normal memory. Dr. Lucia Jacobs from the University of California discovered that the memory region in red squirrels' brains grows in the fall when food is being cached. While other small mammals experience brain shrinkage in winter, red squirrels expand their brains. While gray squirrels make do with remembering the locations of hundreds of nuts, red squirrels cache up to 15,000 cones and must remember each one. Tonight we'll examine how the red squirrel remembers where it stored all those cones and why scientists still struggle to explain this cerebral impossibility. If this mysterious memory ability fascinates you as much as it does me, don't forget to like and subscribe. In the comments, write where you're watching from, what time it is there, and share what surprises you most about the red squirrel. You're the reason we keep exploring nature's secrets. Thank you for being here. First, let's note that researchers don't fully agree on the findings we'll be discussing. Some information is not definitive. Now, let's begin to discover the secrets behind red squirrels' extraordinary food caching abilities. That winter morning in Algonquin Park wasn't the only impossible thing we witnessed. Forest researchers across North America have been documenting similar events for decades. A squirrel approaches on a snow-covered slope. There are no visible markers. There's no distinct scent trail in the frozen air. The squirrel stops, tilts its head, then starts digging. Within seconds, the squirrel emerges with buried pine cones. Food caching is an innate behavior displayed by many animals. They retrieve the food later when needed, just like we stock our refrigerators. But red squirrels don't do this the normal way. We're dealing with a memory that challenges what we know about the mental capabilities of small mammals. Most rodents struggle to remember where they cached food after a few weeks. Red squirrels operate on an entirely different scale. They cache thousands of food items across an area between 2 to 5 acres, and months later, they retrieve them with an accuracy that rivals GPS technology. Think about your own memory for a moment. You lose your keys, you forget where you left your phone. Now imagine you cached 15,000 food items across an area larger than 3 football fields and then found each one 6 months later in complete darkness under 3 feet of snow. That's what red squirrels do every year. But things get stranger here. The brain changes we mentioned in the introduction don't happen in other species. Gray squirrels, the closest relatives of red squirrels, don't show this seasonal brain expansion. Similarly, chipmunks or ground squirrels don't show it either. This change only occurs in red squirrels. Dr. Lucia Jacobs spent years trying to understand this phenomenon. Her team in California tracked squirrel brains across several seasons. What they found changed how we understand brain changes in wild animals. The hippocampus, the brain region responsible for spatial memory, grows substantially every fall, not slightly, significantly. Compare this to what we see in gray squirrels. They use a different strategy called scatter hoarding. Each nut is buried in a separate hole. There are hundreds of separate caches around the home. Gray squirrels retrieve between 70 to 95% of their buried food. This seems impressive until you account for the scale difference. Red squirrels don't scatter hoard, they larder hoard. They cut unripe cones and cache them. 15,000 cones, sometimes more. Over time, these larders grow. Some are passed down through generations for hundreds of years. Each generation expands the larder further. Now let's compare red squirrel memory with gray squirrel memory. A gray squirrel has to remember hundreds of locations, but a red squirrel has to remember the locations of multiple larders, thousands of food items within each larder, and all the backup larders. The memory load is much higher, and winter makes everything harder. Squirrels don't hibernate like other creatures during winter months, so they need food in winter. But finding food in winter is very difficult. During these times, cached food provides the squirrels nutrition. In winter, snow covers the forest floor. Temperatures drop below zero. Scent molecules become nearly undetectable in cold air. Visual markers disappear under white blankets. Yet squirrels continue to find their larders, not by accident, not by luck, with precision. We've watched them dig directly through snow to buried food, without exploratory digging, no trial and error. They go straight to that spot in one attempt, even if that spot is 3 feet deep, completely covered in snow. How is this possible? For years, researchers thought scent was the main factor. Squirrels have an excellent olfactory system. In 1978, German zoologist Herbert Wiltawski tested this in his experiment. He observed that squirrels could smell buried nuts from 12 inches away. They can't smell farther than that. But food larders are deeper. This means squirrels use scent only as a final confirmation. So how do squirrels flawlessly remember a larder they buried in a forest that looks completely different with snow 3 months ago? Memory. Spatial memory. The kind of memory that builds detailed mental maps of the entire territory. Dr. Jacobs and her colleague Emily Lyman conducted experiments that revealed this mechanism. They gave captive grey squirrels 10 nuts to bury. A few days later, they released each squirrel back into the area and watched them collect. The squirrels found more of the food they themselves had buried, so they remember the nuts they buried much better. Moreover, when retrieving, they followed completely different paths from the ones they took when burying. Researchers concluded that squirrels find their cached food by remembering, not by smelling. Think about this for a moment. The squirrels weren't retracing their steps. They weren't following memorized routes. They were setting cues for remembering. They were planning optimal routes between multiple cache areas, which means they have mental maps showing the locations of all the food they buried. We call this mental mapping. You use it every day without realizing. The store is 2 blocks from your home. The park is near the store. You can plan routes that efficiently visit both locations. Red squirrels do the same thing, but with thousands of cues instead of just a few familiar buildings. Squirrels cache food in clusters. This makes remembering easier. Landmarks are crucial in this system. Trees are important as cues, large rocks, fallen logs, the shape of the terrain. Squirrels memorize these features when they cache food. Then winter comes and snow changes everything, but the main landmarks are still visible. The big oak stands in the same spot. These fixed points support the mental map, even when fine details are lost. In winter, when the squirrel searches for the larder, it narrows the search area using landmarks. It approaches where its memory tells it to. Then at close range, scent kicks in. The nose detects faint odors filtering through the snow. The squirrel starts digging. 20 seconds later, food emerges. This is a 2-stage system. Memory for long-range navigation, scent for final confirmation. The two work together, compensating for each other's shortcomings, and the result is quite remarkable. Recovery rates range from 26% in high food abundance years to 95% in food scarcity years. When survival depends on cached food, squirrels find them. They have to find them. But memory and scent aren't the only tools used in this process. Red squirrels use a mental strategy researchers call chunking, which is a technique that allows humans to organize information in the brain. Instead of remembering 15,000 different locations, squirrels group similar items together. All spruce cones go in one part of the larder, all fir cones in another part. This organization reduces memory load and increases retrieval accuracy. Dr. Jacobs observed this behavior in fox squirrels, close relatives of red squirrels. Squirrels bury the same type of nuts close to each other, forming clusters. When they return, they can predict what type of food they'll find based on location. This arrangement shows that categorizing information makes finding food easier. Now here's where the story takes an unexpected turn. All this effort for memory and caching makes no sense if someone steals your food. And in the forest, theft is common. When squirrels cache food, they have to think not just about remembering, but also about security. If rival squirrels see the larders, they can steal them. In one observation, 266 food caching events were tracked. Within the first 2 hours, 10% had moved. Most of this had relocated because it was stolen by other animals. A small portion was done by the squirrel itself, probably because it thought the food was too conspicuous. In the field, deceptive protective behaviors were also observed. Mike Steele's research team found that squirrels make fake caches if rivals are nearby. They do all the movements. They dig a hole, act like they're dropping a nut, carefully cover the empty hole. The result looks the same as real caching, but there's no food in the ground. This is a tactic to waste potential thieves' time and energy. At the same time, they take precautions when they actually bury food. When burying food, they don't orient toward the suspicious animal. Squirrels also spend more time camouflaging their real larders if they sense there are rivals. They bring additional leaf litter to cover the disturbed soil. They return later to make sure their larders haven't been tampered with. If they think there's a theft risk, they dig up the food and move it to a safer location, usually under dense shrubs or in muddy areas where other species find it difficult to dig. Similarly, squirrels spend more time and are more careful when caching food. They prefer more, like hazelnuts. Just like us, we spend considerable time hiding our valuable possessions and choose the most secret places. This flexibility shows that the choices squirrels make are calculated, taking risk and reward into account. The squirrel weighs the energy expenditure in caching against the probability of theft. High-quality nuts are moved to safer locations in areas with high theft risk. Low-quality items are quickly buried in low-risk areas without complex camouflage. Squirrels constantly assess risks, and every food caching decision is made according to this assessment. All these burdens fall on the memory system. The mental load is dazzling, yet red squirrels manage this load every season, every year, and survive the winters that could kill them with their cached food. But memory alone isn't enough. They need something else to survive. Something that will allow them to escape danger in seconds. Something that will move them through the forest depths at extraordinary speeds. Chapter 2. These memory skills have kept squirrels alive throughout winter. But remembering where food is doesn't help if you can't move through the forest. And red squirrels move in ways that seem to violate the laws of physics. Imagine an animal 10 inches long. Weight, slightly more than half a pound. Body length, including tail, approximately 12 inches. Now think of that same creature launching itself and clearing 6 feet in height. Without a running start, just standing still with pure power. We've measured this jump in controlled studies. The numbers always came out the same. Red squirrels can jump vertically up to 7 feet high. This means they're jumping 8 times their own body length upward. Scale this to human proportions. The average person is 5 foot 9 inches tall. 8 times that puts you 46 feet high in the air. That's a 4-story building. You're standing on the ground. You crouch, you jump, and suddenly you're level with 4th floor windows. Red squirrels do this regularly. We've watched them leap from ground level to branches at heights that seem impossible. No ladder, no climbing. Researchers from the University of California studied squirrel jumps to understand exactly how they leap. They tested squirrels jumping in many different environments. Results showed that squirrels adjust their jumps according to different environments. Horizontal jumping is also impressive but works with different mechanics. Researchers measured maximum jump distance by gradually placing baited food farther away. Richard Thornington documented that grey squirrels jump a maximum of 8 feet. Red squirrels, smaller and slightly less powerful, manage to jump between 6 to 7 feet, sometimes more. Think about the calculation that happens in that moment right before the jump. The squirrel is sitting on a branch. The target branch appears in empty air. Now they need to adjust the jump. They look at the distance. They look at the branch they're jumping to. They look at their current energy. Finally, after checking the environment, they jump. This entire process happens within seconds, probably less, before the animal commits to a jump. Usually after a few jumps they achieve perfect precision. But they don't always perform this well. If the jump is miscalculated, it can mean death. But squirrels think about this too. If they miscalculate, they rely on their claws. When they miss, they hold on very well and don't fall. How is this possible? What allows such a small animal to generate such disproportionate power? Let's start with the legs. A red squirrel's hind legs have extraordinary muscle mass relative to body size. Muscles specifically optimized for explosive power. When the squirrel crouches before jumping, these muscles compress like a spring. But muscle alone doesn't explain the whole picture. Ankle joints have unusual flexibility, almost 180-degree rotation. This means a squirrel can turn its hind feet backward while airborne, reversing the direction of the jump. You can observe this behavior when squirrels descend from trees head first. Most animals can't do this. Cats climb trees easily, but have trouble descending because their claws can only bend in one direction. They have to come down backward, slowly and awkwardly. Squirrels just rotate their ankles and run head first down trees at the same speed they run up them. The claws themselves also deserve attention because these sharp claws enable squirrels to reach explosive speeds. Trees are like racetracks for squirrels. They reach incredible speeds of 20 miles per hour. These claws also have perfect gripability. We've documented squirrels climbing brick walls, metal poles, and smooth-barked trees with no grip points. The combination of claw grip and muscle strength allows them to find traction where other animals would slip. And once they start moving, momentum carries them upward at impressive speeds. Squirrels are safe in the treetops while moving at these speeds, but speed can't prevent everything. In the Amazon rainforest, harpy eagles hunt in that same world with extraordinary visual acuity. Even within the dense canopy, they can notice a small shadow moving between branches. From thousands of feet away, they can see a squirrel moving through dense foliage. In our next video, we'll discover this extraordinary vision of harpy eagles and how they hunt. But for now, let's get back to squirrels. Okay, we've talked about how the squirrel decides to jump and how it jumps. So what happens after the squirrel does this? The tail becomes critical here. That bushy tail isn't decorative. During a jump, the tail is held horizontally, directly behind the body. It acts like a parachute, controlling the fall while descending. While running, it helps the squirrel change direction quickly. Watch a squirrel in mid-jump. You'll see the tail making small adjustments. A leftward movement shifts the body right. These corrections happen faster than conscious thought in humans. The squirrel's nervous system processes balance information from the inner ear and makes automatic adjustments through tail position. It keeps the body oriented correctly for landing. The tail also pumps during jumps. The squirrel moves it up and down in a rhythmic pattern. While research suggests this pumping motion may help create additional forward thrust, the physics are still debated. What's clear is that squirrels with damaged tails show decreased jumping accuracy and distance. This confirms the tail doesn't just help maintain balance. Landing mechanics are as important as launch mechanics. First, the front paws reach forward to contact the target branch, claws extending to grip. The hind legs engage a few milliseconds later. The spine compresses slightly, acting like a shock absorber. All these landing movements distribute force across multiple muscles, protecting bones from breaking. We've observed squirrels falling from significant heights, sometimes 30 feet or more, and landing with no apparent damage. This resilience comes from their small size and the physics of scaling. Small animals have a larger surface area relative to their bodies, which creates more air resistance when falling. A squirrel falling from 30 feet has a lower fall velocity and smaller body mass than a human falling from the same distance. And this doesn't mean falls are safe. Squirrels can and do fall, especially onto hard surfaces like concrete. One observer watched a squirrel fall from a great height, then immediately get up and run. So their survival rate from accidental falls is quite high, and they spend a significant portion of their time very high in trees. Field observations have shown that red squirrels regularly spend time at the top of trees, in forests with tall coniferous trees like spruce or pine. We've documented individuals foraging at heights of 100 feet or more above ground. These heights provide advantages. Predators are rare in the upper parts of trees. Food sources like pine cones concentrate in high branches where sunlight is abundant. Visibility extends farther, allowing early predator detection. Treetops are windy but safe if you can navigate thin branches swaying in the wind. Navigating these heights requires everything we've discussed: powerful jumps between branches, strong grip on trees, accurate distance assessment. One mistake could mean a fall that could be fatal. Yet squirrels do this routinely. They spend hours in areas where humans wouldn't survive without climbing equipment and safety harnesses. The three-dimensional nature of their environment also creates unique challenges. Let me explain why I say three-dimensional. Ground-dwelling animals move two-dimensionally, forward-backward and left-right. For tree-dwelling animals, vertical is added up-down. This third-dimensional nature multiplies the complexity of memory. It's not enough for a squirrel to remember where things are horizontally, they also need to remember how high up they are. And different tree species present different challenges. Oaks have thick branches and rough bark, providing excellent grip but requiring longer jumps between limbs. Smooth-barked trees demand additional claw force. Dead trees are unpredictable, with branches that can break without warning. Squirrels learn the characteristics of every tree in their territory and adjust their movement strategies accordingly. But all this climbing ability and jumping power serve a function beyond moving through the air. These skills provide squirrels with access to food, escape from predators. These abilities kept them alive, but survival required more than speed and strength. They needed shelter. Shelter that would protect them from winter storms and summer heat. Red squirrels build architectural structures so carefully designed that researchers still can't understand how such a small brain designs such complex structures. Some shelters have been in use for more than 200 years, passed down from generation to generation. How? Chapter 3. Those climbing skills gave squirrels access to the entire forest. Every branch became a potential pathway. But pathways alone don't provide shelter. You need a home. And red squirrels build homes that rival human engineering in their sophistication. We discovered something remarkable when researchers placed a hidden camera inside a nest box back in February 2012. A wild red squirrel found the box empty and decided to build there. Over 3 days, the camera recorded every moment of construction. What we saw challenged our assumptions about animal architecture. The squirrel made 67 trips carrying material. Each trip brought twigs, bark strips, moss, or grass. No blueprint existed, no instruction manual. Yet the final structure emerged as a perfect sphere, densely woven, weatherproof, and insulated. Total construction time logged at 3 hours and 36 minutes of active work spread across those 3 days. Here's what makes this impossible. The squirrel was alone. No other squirrels helped. No adult taught the technique. Hand-raised squirrels that never saw their parents build nests still construct drays at 6 weeks old. The behavior is innate, coded somewhere in their genetics, expressing itself without learning or observation. How does an animal know how to weave branches into a sphere without ever being taught? We need to talk about what these structures actually are. Red squirrels build 3 distinct types of nests, each serving different purposes through the year. Understanding the differences reveals how much thought, if we can call it that, goes into squirrel architecture. Summer drays are the simplest. Think of them as platforms rather than enclosed structures. The squirrel weaves together a shallow base of twigs, maybe lines it with a bit of moss, and that's sufficient for warm weather. These platforms sit in tree branches, often quite exposed because overheating is more dangerous than cold during summer months. Air circulation matters more than insulation. Winter drays are completely different animals. These structures measure roughly 12 inches in diameter, about the size of a basketball, sometimes larger. The outer shell consists of interwoven twigs and bark strips, creating a rigid framework. Inside that framework, the squirrel packs layers of moss, dry grass, shredded bark, and sometimes feathers if available. The innermost chamber, where the animal sleeps, might be only 4 inches across, but it's surrounded by inches of insulating material on all sides. We've measured temperature differences between inside and outside winter drays. On nights when air temperature drops to -10 degrees Celsius, around 14 degrees Fahrenheit, the interior of a well-built dray maintains temperatures 20 to 30 degrees Celsius warmer. That's a difference of 36 to 54 degrees Fahrenheit just from passive insulation. No heating system, no energy input, just smart material. Selection and construction technique. Breeding drays fall somewhere between summer and winter versions. They need more insulation than summer platforms because newborn squirrels can't regulate their own body temperature, but they don't need as much bulk as winter drays because breeding happens in spring when temperatures are moderate. The female builds or renovates a dray specifically for giving birth, often adding extra soft materials to the interior as the birth date approaches. Location matters as much as construction. Red squirrels typically build drays between 80 and 130 feet up in trees. That height puts them above most ground predators but below the thin branches at the very top that might break under weather stress. The preferred spot is where a large branch meets the trunk, creating a stable fork that won't sway excessively in wind. We've observed drays built directly against tree trunks, wedged into the angle where three branches diverge. These positions provide maximum structural support. The dray essentially rests on solid wood rather than relying solely on the woven framework to bear weight. Conifer trees are preferred over deciduous ones, particularly spruce and pine, because the dense needle coverage provides additional protection from rain and wind. But here's where the story takes an unexpected turn. We thought each squirrel built one nest and lived there. Then radio tracking studies revealed something different. Each squirrel maintains multiple drays scattered throughout its territory. Not 2, not 3, anywhere from 2 to 8, with an average of 4 nests per individual. Why would an animal invest that much energy building homes it doesn't use full time? Peter Lurd spent years tracking red squirrels through conifer plantations in northern England. His radio telemetry data showed squirrels switching between nests regularly, sometimes using a different dray each night for a week before returning to a preferred main nest. Other nests sat unused for weeks, then suddenly became primary residences for a month. The pattern seemed random until we looked at context. Predator pressure explains some of this behavior. If a pine marten discovers one dray and investigates it, the squirrel abandons that nest temporarily and moves to an alternate location. Spreading nests across the territory means a predator can't learn where the squirrel sleeps and stake out that location. Unpredictability becomes a defense mechanism. Parasite load drives other nest switches. Fleas accumulate in drays over time. The warm, protected environment provides ideal breeding conditions for these parasites. When flea populations become intolerable, the squirrel simply moves to a clean nest and lets the old ones sit empty for weeks while the fleas starve without a host. Eventually, the infestation dies off and the nest becomes usable again. Seasonal changes matter too. A dray that's perfect for summer might be too exposed for winter. A winter dray that's heavily insulated might be too hot in July. Rather than rebuilding the same nest twice a year, squirrels maintain a portfolio of structures optimized for different conditions. They rotate through these nests as weather and needs change. Breeding females with young have additional reasons for multiple nests. If something disturbs the natal dray, if a predator investigates too closely or humans come too near, the mother moves her babies. She carries each kit in her mouth one at a time to an alternate nest prepared in advance. We've documented females moving entire litters in under an hour when they perceive danger. This backup system requires planning. The alternate nest must already exist and be in good condition. You can't build a new dray while carrying helpless infants. So females maintain extra nests specifically for this contingency, checking on them periodically to ensure they remain intact and dry. The construction process itself follows a pattern we can now recognize from that hidden camera footage. First, comes the framework phase. The squirrel brings thick twigs and weaves them into a rough sphere, working from multiple angles to create a stable cage structure. This takes the most time and requires the most material transport trips. Once the framework exists, the squirrel shifts to filling and insulation. Softer materials like moss, grass, and shredded bark get packed into the spaces between twigs. The animal works from outside to inside, gradually creating layers of insulating material. The entrance hole, typically facing the trunk for protection from weather, is the last element to be finalized. Captive squirrels can complete this entire process in 12 hours. Wild squirrels take 2 to 5 days because they're also foraging, watching for predators and defending territories. The construction happens in bursts of activity rather than continuous work. But the end result is identical, a weatherproof sphere that maintains its integrity through storms that would destroy simpler structures. Tree cavities offer an alternative when available: a hollow in an old tree trunk, a woodpecker hole enlarged by decay, even an artificial nest box placed by humans. These natural cavities provide better protection than exposed drays, and squirrels prefer them when possible. But large cavities suitable for squirrels are scarce in most forests. Competition is fierce for these prime real estate locations. So most squirrels rely on drays they build themselves, and these structures face constant threats. Winter storms bring heavy snow that can collapse improperly built nests. Ice accumulation adds weight that branches can't support. Wind gusts catch the spherical shape like a sail and tear nests apart or knock them from their anchors. We've found dray remains on the forest floor after major storms. Sometimes the squirrel survives and builds a new nest. Sometimes we find the squirrel dead among the wreckage, killed by the fall or exposure. Young squirrels in their first winter are particularly vulnerable. Their construction skills haven't been perfected through experience. Their drays might look adequate, but fail under stress. Human activity creates additional hazards. Tree trimming in urban areas often removes branches that hold squirrel nests. The people doing the trimming might not notice the dray until the branch crashes down. If babies are inside, they fall with it. Mother squirrels sometimes retrieve fallen young if they're unharmed, but many don't survive the impact. Despite these risks, the dray system works. Millions of red squirrels survive harsh winters inside structures they built with nothing but instinct and available materials. The architecture might not look sophisticated to human eyes, but it solves the same problem we solve with insulated houses and heating systems. Protection from cold, wind, and precipitation, a place to sleep safely, a shelter for raising young. But a nest was useless without provisions inside it. And gathering provisions for months of winter required a strategy far more complex than simply collecting food. It required understanding when to harvest, where to store, and how to defend against an army of thieves waiting to steal everything you worked to gather. Chapter 4. Those nests provided shelter through the long northern winters. Inside the insulated sphere, a squirrel could sleep through -20-degree nights and wake without frostbite. But shelter alone doesn't prevent starvation. Food becomes scarce when snow covers the ground for 6 months. Trees stop producing, nothing grows. Survival depends entirely on what you stored before winter arrived. Red squirrels approach food storage differently than their grey cousins. We've watched both species preparing for winter, and the contrast reveals two completely separate philosophies about risk and resource management. Grey squirrels scatter their wealth. They bury one nut at a time in shallow holes across their home range, sometimes hundreds of separate caches spread over several acres. If a thief finds one cache, the loss is minimal. The strategy distributes risk, ensuring that no single disaster can eliminate the entire food supply. It's the biological equivalent of not putting all your eggs in one basket. Red squirrels take the opposite approach. They concentrate everything in one location, or rather, a few locations. These storage sites are called middens, and they become the center of a red squirrel's world. Picture a pile of cone scales beneath a spruce tree. The pile measures 30 feet across and 3 feet deep at the center. Generations of squirrels have used this spot for storage, each adding their harvest to the accumulation. Some middens contain debris from hundreds of years of use, layers upon layers of discarded scales, marking the feeding sites of ancestors long dead. The fresh cones, the ones that will feed this year's resident, sit buried within this massive structure. The squirrel creates chambers underground beneath the midden pile or in protected spaces among the roots. Green pine cones get cached there by the thousands. 15,000 is common. Some ambitious individuals collect more. This concentration of wealth creates obvious problems. A grey squirrel who loses one cache to a thief has hundreds more scattered elsewhere. A red squirrel whose midden gets raided can lose everything. The entire winter food supply sits in one defendable territory. If you can't defend it, you starve. So red squirrels defend with intensity that seems disproportionate to their size. We're talking about animals weighing 7 to 9 ounces, barely half a pound. They challenge animals 10 times their weight. Grey squirrels flee when red squirrels attack, despite having clear size advantage. The fury of a red squirrel protecting its midden overwhelms the caution of larger competitors. The defense starts with sound. Red squirrels vocalize constantly during territorial encounters. They produce a rapid chattering call that sounds almost mechanical, like shaking a box of matches. The call announces presence and warns intruders. If warning fails, the squirrel escalates to buzzing, a harsher sound that precedes physical attack. The tail pumps up and down. The body tenses, small feet stamp against the branch. Most competitors leave at this point. The cost of fighting a determined defender exceeds the value of stealing a few cones. But some thieves are bold or desperate enough to test the squirrel's resolve. Then physical confrontation begins, usually brief, but occasionally vicious. Bites to the ears and flanks draw blood. Falls happen when combatants grapple on branches. We've found squirrels with sections of tail missing, likely lost during territorial battles. Yet despite these costs, the larder hoarding strategy succeeds. It must, or evolution would have abandoned it. The advantages outweigh the risks when you examine the details. Timing explains part of the success. Red squirrels don't wait for cones to ripen. They harvest green cones in August and September before the scales open and release seeds. A closed cone is a sealed package. The seeds remain fresh inside, protected from moisture and fungi. An open cone scatters its seeds, making collection time-consuming and wasteful. By harvesting early, red squirrels monopolize the crop before it becomes accessible to other species. This creates a narrow window of frantic activity. White spruce cones mature in late July. By early August, red squirrels begin cutting them from branches. The cones fall to the ground with soft thuds, dozens per day when the crop is good. The squirrel descends and carries them one by one to the midden, building the cache that will sustain life through the coming months. We've watched this collection process during peak season. A squirrel might transport 200 cones in a single day, making hundreds of trips between tree and midden. The work continues from dawn until dusk with only brief pauses. There's urgency in the movement, and understanding that time is limited and the task enormous. Other squirrels watch from neighboring territories, waiting for any lapse in attention that might allow theft. The midden itself serves multiple functions beyond simple storage. The pile of old cone scales creates a microclimate underneath. Humidity stays higher beneath the debris, keeping cached cones from drying out. Temperature remains more stable, avoiding the freeze-thaw cycles that damage seeds. Fungi grow in the moist environment, but squirrels seem to prefer cones with slight fungal growth, possibly because the fungi make seeds easier to extract from the cone. Storage isn't limited to cones. Red squirrels cache mushrooms by impaling them on branches and letting them dry in the sun. Dozens of mushrooms might hang from a single branch, creating what looks like strange decorations. The drying process concentrates nutrients and prevents spoilage. Weeks later, the squirrel returns and consumes the dried mushrooms, which have become lightweight and easy to transport. Some mushroom species would kill a human. Amanitas contain toxins that destroy the liver. Yet red squirrels eat them without harm. Their digestive systems process compounds that are deadly to us, extracting nutrition from fungi we can't touch safely. This ability expands their food options during seasons when pine cones alone wouldn't provide sufficient calories. Tree sap offers another resource red squirrels exploit with remarkable cleverness. Sugar maples contain sweet sap in early spring, around 2% sugar when it first flows. That's too dilute to be worth drinking. But red squirrels have learned to modify the system. They bite through bark to puncture the xylem vessels that carry sap. Then they leave and come back hours later. In that time, water evaporates from the wound, concentrating the sugar. When the squirrel returns, it licks sap that's reached 55% sugar content, basically maple syrup produced by patience and evaporation. This behavior shows planning that extends beyond immediate needs. The squirrel creates the wound in the morning, does other activities through the day, then returns to harvest the concentrated sap. It's tool use in a sense, modifying the environment to produce food that wouldn't naturally exist in that form. And it happens in spring when cached food is running low and fresh growth hasn't yet appeared. But all this effort collecting and storing food creates one massive problem. You're not the only one who wants it. Every squirrel neighbor knows where your midden sits. Gray squirrels watch from the edges, waiting for opportunities. Corvids, those intelligent blackbirds, remember cache locations and return when the squirrel isn't watching. Even bears will dig into middens if they find them, scattering hundreds of cones and destroying months of work. Cache pilfering happens constantly. We've documented theft rates approaching 30% in areas with high squirrel density. That means nearly 1 in 3 cones you spent energy collecting and transporting will get stolen before you can eat it. The loss represents wasted effort and reduced winter survival odds. Red squirrels respond with counter strategies. They build multiple smaller caches in addition to the main midden, distributing some risk after all. These satellite caches hold backup supplies, insurance against total loss if the main midden gets raided. The locations change seasonally, and the squirrel checks them periodically to ensure they remain intact. We've also observed squirrels moving their middens entirely when theft pressure becomes too high. The animal excavates cones from the old midden and transports them to a new location, dozens of trips carrying food across its territory to a spot where competitors haven't yet learned to look. It's exhausting work, but preferable to letting thieves consume everything you've gathered. Fake caching appears here too, just as it does in scatter hoarders. When corvids or other squirrels are watching, a red squirrel might carry a cone toward the midden, then veer off and pretend to cache it somewhere else. The performance wastes the observer's time if they investigate the false cache, and it might divert attention from the real storage site. Deception becomes part of the economic warfare that defines relationships between competing food storers. These battles over stored food will intensify as winter arrives and fresh resources disappear. But the fighting happens on a three-dimensional battlefield where movement means everything. Speed and agility determine who reaches the cache first, who escapes with stolen food, who catches the thief. And that movement requires abilities most animals never develop, skills that make the forest canopy a highway system accessible only to specialists. Chapter 5. That stored food sat waiting beneath the midden pile. Thousands of cones cached in chambers among the roots. Everything needed for winter survival concentrated in one defended space. But defense required constant movement. A stationary squirrel is a vulnerable squirrel. Territory boundaries needed patrolling. Thieves needed chasing. And all of that happened not on flat ground, but in the tangled, three-dimensional world of the forest canopy. We tend to think of movement as something that happens along surfaces, walking, running, crawling. Even jumping feels like moving from one surface to another. But watch a red squirrel for an hour and you realize they inhabit a completely different kind of space. They spiral up tree trunks without slowing, they leap between branches that sway in different rhythms, they hang upside down from bark that looks too smooth to grip. They reverse direction mid-climb, rotating their bodies around the trunk as if gravity applies differently to them than to everything else around them. The forest canopy becomes a highway system with routes that exist in all three dimensions simultaneously. Ground speed tells part of the story. A red squirrel moving across open terrain can reach 12 miles per hour. That's fast for something weighing half a pound. The movement is a series of bounds, the body compressing and extending with each leap, the tail streaming behind for balance. They change direction without losing speed, cutting sharp angles that would tumble most animals. But ground movement is almost incidental for red squirrels. They spend most of their active time above ground, navigating branch networks that shift with every breeze. Up there, speed becomes less important than precision. A miscalculation means falling, and falls from 30 or 40 feet can be fatal even for animals built to survive them. The vertical climb happens with a rhythm you can almost hear if you watch closely. Front paws reach high, claws extending to catch bark. The shoulders pull, lifting the body. Rear legs push from below, adding force. The spine flexes, giving extra reach to each movement. Then the cycle repeats over and over, carrying the squirrel upward at what looks like an effortless pace. What we don't see from the ground is the constant micro-adjustment happening in every joint. The ankle rotates slightly to change claw angle. The wrist flexes to maintain grip on irregular bark. The tail shifts position to counterbalance body weight as the squirrel moves from vertical to horizontal surfaces. Each adjustment is small, barely visible, but together they create movement that appears smooth and controlled. Descending tests different skills. Most animals that climb well struggle coming down. Their joints don't bend the right way for head-first descent. They have to back down slowly, feeling for footholds they can't see, vulnerable to predators that might be waiting below. Red squirrels bypass this limitation entirely by rotating their ankles backward. The rear feet point up the tree even while the head points down, claws still grip. The descent happens at climbing speed, just in reverse. This ability changes everything about how squirrels use vertical space. They don't need to commit to going up. They can climb 50 feet, decide the branch they wanted is actually in a different tree, and come back down just as quickly. The vertical dimension becomes as fluid and accessible as horizontal movement is for ground-dwelling animals. Branch-to-branch travel adds another layer of complexity. Branches move, they sway with wind, they flex under weight. Two branches might be close together when you look at them, but the gap changes moment by moment as each branch responds to different forces. Jumping between moving targets requires prediction, not just measurement. We've watched squirrels pause before difficult jumps. The pause isn't hesitation, it's calculation. The squirrel is observing how the branches move, finding the rhythm, waiting for the moment when launch platform and landing zone align favorably. Wind gusts change the timing, rain makes bark slippery, requiring different claw angles. The squirrel incorporates all of these variables before committing to the leap. Once airborne, adjustments continue. The tail makes small movements that shift the body's trajectory. The front paws reach forward, ready to grab whatever surface arrives first. The rear legs stay tucked initially, then extend just before landing to absorb impact. The whole sequence takes maybe half a second, but it involves coordination between multiple body systems working faster than conscious thought. Landings don't always go perfectly. Sometimes the target branch is thinner than expected and bends sharply under the squirrel's weight. Sometimes the bark is loose and claws don't catch immediately. We've seen squirrels scramble on landing, working to secure grip before momentum carries them off the branch. Most of these scrambles succeed. The squirrel stabilizes and continues moving, but occasionally the branch breaks or the grip fails entirely and the squirrel falls. Falls happen more often than you might expect for animals this skilled. Young squirrels learning the canopy fall regularly. Adults fall during territorial chases when attention is on the competitor rather than the route. Branches break unexpectedly, especially dead wood that looked solid from the outside. Each fall is a test of whether the squirrel's body can handle the impact. Small size helps here in ways that aren't immediately obvious. When you fall, air resistance slows you down. How much it slows you depends on your surface area compared to your weight. Small animals have lots of surface area relative to their weight, so they experience more air resistance per pound of body mass. A falling squirrel reaches a maximum speed of around 23 miles per hour, much slower than a human would fall from the same height. That lower speed means lower impact force when the squirrel hits the ground. We've documented falls from 30 feet that the squirrel walked away from without apparent injury. The animal landed, paused for a moment, as if checking whether anything hurt, then scurried off to the nearest tree. Not every fall ends this way, but the survival rate is surprisingly high for impacts that would break human bones. The three-dimensional nature of the canopy also means escape routes exist in every direction. A ground predator approaching from below can be avoided by climbing higher or moving to another tree. A hawk approaching from above triggers descent into denser branches where wings can't maneuver. Threats from the side mean moving around the trunk or leaping to a neighboring tree. The squirrel evaluates which direction offers the best escape and moves there, often faster than the predator can adjust its attack. Three-dimensional movement isn't just for escape, it's also used for hunting. Squirrels can flee from threats in every direction, up, down, sideways. But some predators are even better than squirrels in this three-dimensional space. In the canopy of the Amazon, harpy eagles hunt in that same three-dimensional world. But unlike squirrels, they're on the pursuing side, not the fleeing side. For a winged predator, the treetops work differently, maneuvering between branches, making turns in confined spaces while flying at full speed. In our next video, we'll see how the harpy eagle hunts in this complex environment and how it captures prey with its deadly talons. But for now, let's return to the mental maps of squirrels. This kind of movement requires mental maps that include height information. It's not enough to know that a particular tree contains a food source. The squirrel needs to know which branches provide access, how high those branches are, what route connects this tree to neighboring trees. The map exists in 3 dimensions, tracking hundreds or thousands of branch connections across a territory that might span 2 or 3 acres. We think about this kind of spatial awareness when we watch squirrels move through familiar territory. They don't pause to figure out routes, they just go, following paths they've memorized through repeated use. A branch breaks and the route becomes impassable. Within days, the squirrel has incorporated this change and now uses an alternate path without apparent thought. The mental map updates automatically based on experience. Urban environments test this flexibility. City squirrels navigate power lines, fence tops, building ledges, and rain gutters alongside natural branches. These artificial structures follow geometric patterns that don't exist in forests. Straight lines, right angles, surfaces made of metal and plastic instead of wood. Yet, squirrels adapt within weeks, learning which lines support weight, which surfaces provide grip, where humans have created unintentional pathways between trees that are too far apart for natural jumps. The transition from forest to city must require significant relearning. A squirrel raised in woodland encounters wood, bark, and leaves. Every surface has texture, every branch has some flex. Moving to an urban park means discovering smooth metal poles, rigid plastic tubes, and slick glass windows. The basic skills transfer, but the details all change. Somehow, squirrels make this transition successfully enough that urban populations often exceed rural densities. All of this movement serves the fundamental needs we've discussed: getting to food caches, checking territorial boundaries, escaping predators, building and maintaining nests. Every aspect of survival involves traveling through 3-dimensional space multiple times each day. The athleticism isn't a party trick, it's the foundation of everything else red squirrels do. But even the most skilled athlete faces limitations imposed by season and weather. Winter transforms the forest into something harder and colder. Summer brings different challenges with heat and storms. The strategies that work in spring fail in autumn. Navigation skills remain constant, but how those skills get applied changes month by month as the year cycles through its familiar pattern. Chapter 6. Those navigation skills carried squirrels through the forest in every season. The same branches in winter and summer, the same trees standing through spring and fall. but the forest itself transformed around them month after month as the year turned through its cycle. And with each transformation, the squirrel's life changed too. Winter arrives slowly in the northern forests. The first snow comes in October, light dustings that melt by midday. Then the snow stays longer. It accumulates in shaded areas beneath the conifers. The temperature drops and stays below freezing for days at a time. Other animals respond by disappearing. Ground squirrels retreat underground and sleep for months. Chipmunks curl up in their burrows. Bears find dens and slow their hearts to barely perceptible rhythms. Red squirrels stay awake through all of it. When the temperature drops to 20 below zero, they're still moving through the canopy. When snow piles 3 feet deep across the forest floor, they're still checking their caches and defending their territories. They're among the few mammals that remain active through the entire northern winter without hibernation. This decision, if we can call it that, seems counterintuitive at first. Winter is hard, food is scarce, cold burns through calories just maintaining body temperature. Most small mammals avoid the problem by sleeping, reducing their needs to almost nothing for months. Red squirrels choose to stay awake and deal with winter on its own terms. The choice makes sense when you consider what happens to territories during winter. An animal that hibernates abandons its space for half the year. That space sits empty, undefended. When spring arrives and the hibernator wakes up, it might find another animal has claimed the territory. The midden might be empty, the stored food consumed by someone who stayed awake through winter. Red squirrels avoid this risk by maintaining presence year-round. The territory remains defended, the cache remains protected. When spring arrives, they're already there, already established, ready to take advantage of the season's opportunities, while other animals are just waking up. But staying awake through winter requires adjustments. The squirrel's fur thickens as autumn progresses. The summer coat, which is reddish-brown and relatively thin, gives way to winter fur that's denser and tinged with grey. The grey colouring provides better camouflage against snow and bark in winter light. The thickness traps air close to the skin, creating insulation that reduces heat loss. Ear tufts appear in winter, small pointed extensions of fur at the top of each ear. We're not entirely sure what purpose these serve. They might protect the ear opening from snow and wind. They might play a role in communication, making the squirrel's silhouette more distinctive during territorial displays. Or they might simply be a side effect of the general fur thickening that happens everywhere else on the body. Activity patterns shift with the cold. Summer squirrels forage actively throughout the day, taking only brief rests during the hottest afternoon hours. Winter squirrels concentrate their activity into shorter windows when temperature and light are most favorable. Early morning after sunrise brings the first activity burst. Late afternoon before darkness brings another. The middle of the day, when human visitors are most likely to be walking through the forest, often finds squirrels resting in their nests. These rest periods conserve energy during the coldest parts of the day. The squirrel curls into a ball inside its well-insulated dray, sometimes with its tail wrapped around its body for extra warmth. Heart rate slows. Breathing becomes shallow. It's not hibernation, but it's not full waking activity either. Something in between, a quiet time that stretches through the hours when venturing out would cost more calories than could be gained. Feeding during winter relies almost entirely on the caches established in autumn. Fresh food doesn't exist. Trees are dormant. Nothing grows. Snow covers the ground to depths that make foraging impossible. The squirrel travels from nest to midden, retrieves cached cones, carries them to a favored feeding spot and spends time extracting seeds. The cone scales fall away, adding to the pile that's been accumulating for generations. Another meal consumed, another small victory against the cold. Then spring arrives and everything changes again. Not all at once. Spring is gradual in the northern forest. Snow melts slowly, retreating first from sunny slopes, lingering in shaded areas for weeks. Ice breaks up on streams and ponds. The frozen ground softens, and with these changes a new challenge emerges. The cached food is running low. Months of eating have depleted what seemed like abundant stores in November. Fresh growth hasn't appeared yet. Trees are beginning to wake up, but buds are just forming. Seeds from last year's cones are gone. This period, the gap between winter stores and spring abundance, is when survival becomes most difficult. Red squirrels adapt by expanding their diet. They eat tree buds, stripping them from branches before they can fully develop. They gnaw bark, accessing the thin layer of cambium beneath the outer bark that contains some nutrition. They revisit areas where they might have missed cached items during winter, searching more thoroughly now that desperation sharpens their attention. Some mortality happens during this spring gap, particularly among young squirrels experiencing their first full-year cycle. The ones who didn't cache enough food the previous autumn, the ones whose middens got raided too heavily during winter, the ones who miscalculated their needs. Not all of them survive to see summer, but for those who make it through, summer arrives as a release. Green returns to the forest. Understory plants begin flowering. Mushrooms appear after spring rains. Tree seeds from various species ripen at different times, creating a rolling harvest that extends through the warm months. Food becomes abundant and the pressure eases. Summer activity increases. Squirrels spend less time resting, more time foraging and exploring. This is when territories might shift slightly, when young squirrels who survived their first winter begin establishing their own spaces. This is when breeding happens, when females allow males into their territories briefly for mating, then drive them away and begin preparing nests for the young that will arrive 5 weeks later. The summer forest is noisy with squirrel activity. Territorial calls echo through the canopy. Chases between neighbors become frequent as boundaries get tested and defended. Young squirrels venture away from their mother's territory, looking for unoccupied spaces to claim. The population spreads and adjusts, finding a new equilibrium that will hold through the coming year. Then autumn approaches and the cycle begins again. Cones start appearing on spruce and pine. Green at first, tightly closed, but the squirrels can tell they're there. The collection urge emerges, driven by some internal signal we don't fully understand. Days shorten, temperature begins dropping, and the squirrels start working with an intensity that won't stop until snow covers the ground and the cache is complete. This annual rhythm has repeated for thousands of generations. The pattern is ancient, refined through countless iterations of trial and failure. Squirrels whose internal clocks were poorly calibrated died during winter. Their genes disappeared from the population. The ones who survived passed on timing mechanisms that worked, that triggered caching behavior at the right moment, that balanced energy expenditure across seasons in ways that maximized survival odds. We're watching the result of that long selection process. Every squirrel moving through the forest carries the legacy of ancestors who made the right seasonal decisions at the right times. The timing isn't learned. Young squirrels raised in captivity with no exposure to wild squirrels still begin caching behavior in autumn, even when food remains constantly available. Something internal drives the pattern, something coded deep enough that it expresses itself without environmental cues. The modern forest still follows these rhythms, but changes are appearing around the edges. Winters are warming slightly in many areas. Snow arrives later. Spring comes earlier. The timing that worked for thousands of years is shifting, and squirrels must adjust. Most seem to be managing so far their behavioral flexibility, allowing them to adapt as conditions change. But the long-term effects remain unknown. For now, the cycle continues. Winter to spring to summer to autumn, and back to winter again. Red squirrels move through each season, their behavior shifting to match the demands of the moment. And every day within each season follows its own rhythm, its own pattern of activity and rest that divides the 24 hours into manageable pieces. Chapter 7. Those seasonal rhythms shape the broader patterns of life through the year. But within each season, within each week, a smaller rhythm played out. The rhythm of a single day. Dawn to dusk and back to dawn. A cycle that repeated regardless of whether snow covered the ground or leaves hung green on the branches. Morning arrives quietly in the forest. Light filters through the canopy before the sun itself becomes visible. The air is cool, still holding the chill of night. Dewdrops sit on leaves and needles, catching the early light, and somewhere in the branches above, a red squirrel stirs inside its dray. The emergence from the nest happens gradually. First, the head appears at the entrance hole, checking the surroundings. The squirrel pauses there, sniffing the air, listening. Nothing moves in the dawn stillness. After a moment, the squirrel climbs out onto the branch and sits upright, surveying the territory in the growing light. This morning, check happens every day, regardless of weather. The squirrel needs to know if anything changed during the night. Are there predators nearby? Did a storm knock down branches? Is another squirrel attempting to intrude on the territory? These questions get answered in the first few minutes after waking just by sitting quietly and observing. Then the activity begins. The first task is usually feeding. The squirrel travels to a cache site or to trees where food might be available. Movement is purposeful but not hurried. There's a methodical quality to these morning trips, as if the squirrel is following a mental checklist of locations to visit and tasks to complete. At a cache site, the squirrel digs or retrieves stored food. At a feeding tree, it might harvest seeds from cones or eat buds depending on the season. The feeding process takes time. A pine cone must be stripped scale by scale. Seeds must be extracted and consumed individually. The squirrel sits in one spot for 10 or 15 minutes, working through its breakfast while remaining alert for any signs of danger. After the initial feeding, there's often a pause. The squirrel returns to a comfortable perch, perhaps a thick branch with good visibility, and simply sits. Grooming happens during these pauses. The paws work through the fur, removing debris, smoothing areas that got ruffled during movement. The tail receives particular attention, each section carefully cleaned and fluffed. These grooming sessions serve purposes beyond cleanliness. They're rest periods disguised as maintenance. The squirrel isn't moving through the territory or defending boundaries or searching for food. It's just sitting, working slowly through its coat, letting the morning warmth build as the sun rises higher. Mid-morning brings increased activity. This is when territorial patrols happen, when the squirrel travels the boundaries of its range and checks on important locations. The route varies from day to day but covers the same general areas over the course of a week. Scent marking occurs during these patrols, the squirrel rubbing its cheeks and chest against branches at key locations. If neighbors are encountered during these patrols, interactions are usually brief, a vocal exchange, some posturing, then both animals return to their own territories. Physical conflicts are rare between established neighbors who've already sorted out their boundaries. The displays are more reminder than challenge, a daily reinforcement of agreements that were settled weeks or months earlier. By late morning or early afternoon, activity decreases. The squirrel returns to its nest or finds a shaded spot in the branches and rests. This midday quiet period can last 2 or 3 hours depending on temperature and season. During summer heat, the rest extends longer. During mild spring or autumn days, it might be brief. The rest isn't sleep exactly, at least not the deep sleep that happens at night. The squirrel remains somewhat alert, opening its eyes periodically to check surroundings, but the energy expenditure drops significantly compared to active foraging or territorial patrolling. Heart rate slows. Breathing becomes regular and shallow. The body conserves resources during the hours when being active would cost more than it would gain. This energy management makes sense for animals with high metabolic rates. Small mammals burn through calories quickly, just maintaining body temperature and basic functions. Every movement costs energy. Every minute spent active requires food to fuel it. By concentrating activity into the most productive hours and resting during less favorable times, red squirrels stretch their food resources further. Late afternoon brings a second activity peak. The squirrel emerges from rest and begins another round of foraging and territory checks. This evening session mirrors the morning pattern but often includes additional cache maintenance during seasons when food storage is active. Cones get moved, new caches get created, existing storage sites get inspected to ensure no theft has occurred. The quality of light changes as evening approaches, shadows lengthen, the air cools again. Birds that were active during midday begin settling into their own roosting spots. The forest gradually quiets and the squirrel makes its way back toward the nest, completing a final circuit of the immediate area around the dray before entering for the night. Inside the nest, darkness comes early. The thick walls block most remaining light. The squirrel curls into its sleeping position, tail wrapped around the body, nose tucked close to the chest. This posture minimizes exposed surface area, reducing heat loss during the cold night hours. Within minutes, the squirrel transitions into true sleep, the kind with lowered consciousness and reduced awareness of surroundings. The night passes quietly. Small sounds might cause brief waking, a momentary lifting of the head to listen, then settling back into sleep when nothing threatening emerges. Storm winds might shake the dray, but the structure holds firm. Rain might patter against the outer shell, but the interior stays dry. The squirrel sleeps through all of it, protected by the architecture it built weeks or months earlier. This daily pattern varies slightly with the seasons, but the basic structure remains constant. Morning activity, midday rest, evening activity, nighttime sleep. The rhythm is bimodal, split into 2 peaks of effort, separated by periods of reduced activity. This pattern appears across many animal species but feels particularly pronounced in red squirrels, where the contrast between active and quiet periods is easy to observe. Urban squirrels show variations on this pattern. City parks have different rhythms than wild forests. Human visitors arrive in late morning and stay through afternoon. Food becomes available when people come to feed the animals. These artificial food sources shift the timing of squirrel activity toward matching human schedules rather than following purely environmental cues. We've watched park squirrels spend more time on the ground than their forest counterparts. The ground in parks is maintained, cleared of heavy underbrush, making travel easier and safer. Feeding stations exist at ground level. People drop food scraps on pathways. All of this draws squirrels down from the canopy for longer periods that would happen in wild settings. The activity peaks shift too. Park squirrels show increased activity during human lunch hours when food scraps become plentiful. They rest less during midday because that's when opportunities appear. Evening activity extends later because artificial lighting keeps the park illuminated past natural dusk. The ancient rhythms adapt to modern conditions, flexibility allowing survival in environments that didn't exist a few centuries ago, but whether in forest or park, whether following natural or adapted schedules, the purpose remains the same. Gather enough food to survive, defend territory against competitors, maintain the nests that provide shelter, avoid predators that would end everything. Each day is a collection of tasks that must be completed to reach the next dawn, and each task requires interaction with the forest community. Red squirrels don't live in isolation. Neighbors occupy adjacent territories, other species share the canopy and compete for resources, predators hunt through the same spaces. The forest is a network of relationships, connections between individuals and species that shape behavior in ways we're only beginning to understand. Chapter 8. That daily routine played out against a backdrop of other lives. The forest held more than just one squirrel following one schedule. Every tree supported territories. Every branch might mark a boundary between neighbors, and those boundaries mattered in ways that shaped each day's activities. Two squirrels meet where territories touch. The meeting happens on a branch that both animals use regularly, a section of oak that extends between their respective core areas. Neither squirrel is surprised to find the other here. They've met at this spot dozens of times before. The first squirrel sits upright. Its front paws come up to its chest in what looks like a boxer's stance. The tail rises over its back. Small ear tufts point straight up. The posture says everything without sound. This is my space. You know this. We've discussed it before. The second squirrel mirrors the posture. Same upright sitting position. Same raised tail. They face each other across maybe 6 feet of branch, two small mammals displaying in the dappled morning light. Then one of them makes a soft chattering sound, barely audible from the ground below. The other responds with its own vocalization. The exchange lasts perhaps 5 seconds. Then both squirrels turn and move back toward their respective territories. No chase, no physical contact. Just a brief reminder of agreements that have held for months or years. The interaction ends as quietly as it began, leaving the boundary branch empty again in the morning stillness. This is how most territorial encounters unfold between established neighbors. The boundaries are known, the relationships are settled. Daily meeting serve only to reaffirm what both parties already understand. There's an efficiency to it, a way of managing conflict that minimizes energy expenditure and injury risk. We call this the deer-enemy effect. Your neighbor is a predictable presence. You know where their territory ends and yours begins. You know their vocal patterns and behavioral tendencies. They represent a known quantity, a manageable relationship. A stranger appearing in the same location would trigger much stronger defensive responses because strangers are unpredictable, potentially more dangerous than familiar neighbors. Researchers tested this by playing recordings of squirrel calls from speakers placed in different locations. When the call came from a neighbor's territory and sounded like that neighbor, the resident squirrel showed mild interest but no aggressive response. When the call came from the same location but sounded like an unfamiliar squirrel, the resident responded with intense territorial behavior, approaching the speaker, vocalizing aggressively, and displaying threatening postures. The difference in response intensity was striking. Neighbors get acknowledgement, strangers get confrontation. The distinction makes evolutionary sense. Challenging every neighbor every day would exhaust both parties with no real benefit. But allowing strangers to establish themselves would mean losing territory to newcomers who haven't earned their place through long-term residence. Territory size varies between individuals. Males typically claim larger areas than females, sometimes spanning 7 or 8 acres in regions where food is scattered. Females maintain smaller territories, often 2 to 5 acres, but defend them more intensely during breeding season when protecting young becomes the priority. The actual defended space isn't uniform across the territory. There's usually a core area, maybe an acre or less, where the squirrel spends most of its time and defends most vigorously. The midden sits in this core area. The primary nest is here. The most frequently used travel routes pass through this space. This is home in the truest sense, the center of the squirrel's world. Beyond the core, there's a larger home range where the squirrel forages and travels, but doesn't defend as intensely. Other squirrels might pass through these peripheral areas without triggering strong responses, especially if they're just moving between their own territories and not attempting to establish residence. The boundaries here are softer, more flexible, subject to negotiation based on food availability and population density. These territories persist through time. A squirrel that establishes itself in a good location might hold that territory for several years until age or injury weakens its ability to defend the space. When a resident dies or disappears, the vacant territory doesn't stay empty long. Neighboring squirrels might expand into the space, or a young squirrel looking for its first territory might claim it within days. Sometimes mothers pass territories to their offspring, though this happens in only a small percentage of cases. The mother might shift to a less desirable adjacent area, allowing her daughter to take over the established territory with its known resources and built infrastructure. This transfer represents significant maternal investment, giving the young squirrel an enormous advantage over peers who must find and defend new territories from scratch. But most young squirrels receive no such inheritance. They must find their own space, which usually means settling for marginal habitat on the edges of established territories or waiting for a resident to die and create a vacancy. First-year mortality is high, with many young squirrels failing to secure adequate territories before winter arrives. Those who succeed join the established population. Those who fail disappear from the forest without leaving descendants. Now, the social structure that emerges from these individual territories is loose but real. Squirrels aren't solitary in the strict sense. They're aware of their neighbors. They respond to each other's alarm calls. They avoid areas where recent aggressive encounters occurred. The forest becomes a patchwork of overlapping ranges and contested boundaries, a community of individuals maintaining relationships through daily interactions and long-term memory. Competition extends beyond other red squirrels. Grey squirrels occupy some of the same forests, particularly in regions where habitat has been altered by human activity. The two species interact with hostility despite the size difference. Red squirrels, though smaller, often drive grey squirrels away from prime feeding areas through sheer aggressive determination. The grey squirrels usually retreat rather than fight, calculating that the resource isn't worth the energy cost of confronting such a fierce opponent. Corvids present a different kind of challenge. These intelligent birds watch squirrels constantly, learning the locations of caches and waiting for opportunities to steal stored food. A raven or crow might follow a squirrel during catching behavior, marking the location, then returning later to excavate the food after the squirrel moves elsewhere. The theft is frustrating but difficult to prevent given the bird's mobility and aerial advantage. Red squirrels respond with counter strategies. They perform fake caching when birds are watching, going through the motions of burial without actually depositing food. They move caches after initial storage if they suspect observation. They chase corvids aggressively when they venture too close to middens, though the birds usually evade easily by flying beyond the squirrel's reach. These interactions create an ongoing economic conflict where each party tries to maximize its own benefit while minimizing losses to competitors. The squirrels work to protect stored resources. The corvids work to exploit those resources without investing the effort of collection. Neither side wins permanently. The balance shifts day by day based on vigilance, luck, and the relative abundance of alternative food sources. Predators add another dimension to the social landscape. Hawks patrol the canopy during daylight hours, scanning for movement below. A squirrel that strays too far into open areas or lingers too long in exposed positions risks being taken. The response is constant vigilance, frequent pauses during travel to scan the sky, preference for routes with overhead cover, immediate freezing when shadows pass overhead, remaining motionless until the threat moves away. Pine martens hunt through the same three-dimensional space squirrels occupy. These agile predators climb as well as squirrels and are large enough to kill them easily. In regions where pine martens are common, squirrel behavior shifts noticeably. They spend more time in the thinnest branches where the heavier martens cannot safely travel. They abandon territories with characteristics that favor predator ambushes. Population density decreases in areas of high marten activity. Owls hunt at night, which should put them outside the squirrel's active period, but squirrels occasionally move during twilight or darkness, especially during summer when nights are short. An owl striking in dim light faces less resistance than a hawk attacking in full daylight. The squirrel's vision isn't optimized for darkness. Reaction time is slower. The advantage shifts to the predator. These predation pressures shape territorial choices. Squirrels prefer territories with good visibility, multiple escape routes, and dense cover when needed. A territory with abundant food but poor sight lines might go unclaimed because the predation risk outweighs the food benefit. The successful territories balance resources against safety, providing enough of both to support survival through multiple seasons. Within this complex social environment, individual personalities emerge. Some squirrels are more aggressive than others. Some are more tolerant of intrusions. Some respond to threats with immediate confrontation, while others assess situations more carefully before acting. These personality differences are subtle but consistent, and they influence how relationships develop with neighbors and how conflicts get resolved. The forest community isn't just squirrels and their competitors, it's a network of relationships extending across species. Woodpeckers create cavities that squirrels use for nesting. Fungi that squirrels eat depend on tree roots. The trees themselves benefit from seed dispersal when squirrels forget cache locations. Everything connects in ways that aren't always obvious from watching individual interactions, and those connections extend into the future. The territorial squirrel defending its boundary today might be fighting to protect resources that will feed offspring not yet born. The cache sites scattered through the territory represent investments that will pay out over months or years. The relationships with neighbors established now will determine conflict levels through the coming seasons. Every action ripples forward through time, but all of these relationships, all of these territorial struggles and daily interactions depend on one fundamental factor: the next generation. Without offspring, territories mean nothing. Cache sites sit empty. The social structure collapses. Everything a squirrel does ultimately serves the goal of reproduction, of creating young who will carry forward the patterns that allowed their parents to survive. Chapter 9. Those territories held through seasons and years. Those boundaries defended through daily encounters. All of it leading toward one outcome: the continuation of life. The raising of young who would someday claim their own spaces in the forest canopy. Late winter brings change to the female squirrel's behavior. She moves differently through her territory, less focused on feeding, more restless. She ventures beyond her usual boundaries, traveling into areas she normally avoids. The trips are brief, exploratory. She returns to her core territory within hours, but the pattern repeats over several days. These wanderings serve a purpose. She's advertising her condition to males in neighboring territories. Her scent changes during this period, carrying signals that males can detect from considerable distances. They respond by increasing their own movements, expanding their patrols, attempting to locate the source of the scent that indicates breeding opportunity. Within a day or two, males begin arriving. They approach cautiously at first, testing whether she'll tolerate their presence. Most times throughout the year, a male entering her territory would be chased away immediately. Now the response is different. She allows them closer. More males arrive, drawn by the same signals. Soon, several males are moving through her territory, following her movements, waiting. The window is brief, one day. That's all the time available for breeding. Her body becomes receptive for perhaps 12 hours, then the opportunity closes. The males seem to understand this urgency. Their pursuit becomes more focused as the day progresses. Chases develop through the branches, multiple males following the female through routes she chooses. The chase might look chaotic from below, but there's structure to it. The female controls the pace and direction. She leads the males through her territory, testing their persistence and physical condition. The chase continues for hours, moving through different levels of the canopy, across gaps between trees, along branches that require precise jumping. It's exhausting for all participants. Eventually she stops and allows one male to approach, sometimes the same male who was most persistent during the chase. sometimes a different male who happened to be in the right position when she decided to stop. The mating itself is brief, perhaps 15 or 20 seconds. Then she moves away and the chase might resume, with other males attempting their chances. By the end of that single day, multiple males have likely bred with her. Then her receptivity ends. She becomes aggressive again toward males, driving them from her territory with the same intensity she shows toward any intruder. The males depart, returning to their own territories. They played their role. Everything from this point forward happens without them. The female returns to normal routines. Feeding, territory maintenance, rest periods in her nest. Nothing in her appearance suggests that anything significant occurred. For 5 weeks this continues. The pregnancy progresses invisibly. Her body changes internally, but externally she looks and acts like any other adult squirrel. Then she begins preparing a natal nest. She might renovate an existing dray, adding fresh material and soft lining, or she might build a new structure specifically for birthing. The work takes several days. Extra moss gets collected, fine grass gets shredded and arranged. She tests the nest repeatedly, entering and settling into position, checking that everything feels right. The young arrive in early spring, usually late March or early April. 3 to 6 in a litter, though 4 is most common. They're born tiny and helpless. No fur covers their pink skin. Eyes remain sealed shut. Ears are closed. Each weighs roughly 1/3 of an ounce, barely 10 grams. They can't regulate their own body temperature. Without their mother's warmth, they would die within hours. She curls around them inside the nest, her body providing the heat they need to survive. They nurse frequently, their mouths finding her nipples by scent and instinct. The milk provides nutrition and antibodies that protect against diseases they haven't yet encountered. Between feeding sessions, she licks them clean, stimulating their digestion and removing waste. For the first week, she barely leaves the nest. Brief exits for her own feeding, quick trips that last 10 or 15 minutes. Then she returns to her young. The nest stays dark and warm. The kits sleep between feedings, their tiny bodies growing steadily. By the end of that first week, dark fur begins appearing on their backs. The second week brings more changes. The fur thickens and spreads. Their bodies gain weight, doubling their birth size. They still can't see or hear, but their movements become more coordinated. They begin to crawl short distances within the nest, exploring the small space that constitutes their entire world. Week 3 marks the emergence of teeth. Small white points appear in their gums, the beginnings of incisors that will eventually grow throughout their lives. The mother's feeding trips become longer now, her own needs increasing as the young require more milk. She might leave for 30 minutes at a time, trusting the nest's insulation to keep her offspring warm during her absence. By week 4, ears begin opening. The kits start responding to sounds, their heads turning toward noises outside the nest. Eyes remain closed, but the seal is weakening, the lids preparing to separate. Movement inside the nest increases. The kits wrestle with each other in clumsy play that helps develop their muscles and coordination. Week 5 or 6 brings the moment when eyes finally open. The world appears for the first time. Light filters through the nest entrance. Shadows move against brightness. The kits blink and stare, their brains processing visual information for the first time. Within days, they're focusing on objects, tracking movement, beginning to understand the space around them. At 6 weeks, they're still nursing, but also starting to sample solid food their mother brings to the nest. Small pieces of seeds, soft plant material. The kits mouth these items, learning textures and tastes, though most of their nutrition still comes from milk. Their fur has filled in completely now. The ear tufts are visible. They look like miniature versions of adult squirrels. Week 7 or 8 marks the first ventures outside the nest. Tentative at first. A kit pokes its head through the entrance hole and freezes, overwhelmed by the openness beyond. The mother might be nearby on the branch, calling softly, encouraging. Eventually, the kit climbs out onto the branch and clings there, unsure what to do next. Those first trips outside last only minutes. The kit explores the immediate area around the nest entrance, touching bark with its paws, testing its grip. Then it retreats back inside where everything is familiar and safe. Over the following days, the trips extend. The kit moves farther from the nest. It follows its mother on short journeys through nearby branches. The young watch everything their mother does, how she moves through branches, where she finds food, how she opens cones to extract seeds. They attempt to mimic her actions, often failing at first but gradually improving. Learning happens through observation and practice, the kits acquiring skills they'll need for independent life. Play occupies much of their time during these weeks. They chase each other through the branches, they wrestle on stable platforms, they practice jumps between small gaps. The play looks random, but it develops crucial abilities: balance, coordination, distance judgment, all the physical skills they'll need for survival. The mother still nurses them, but less frequently. They're eating more solid food now, finding items on their own, learning which things are edible and which should be avoided. Their teeth are sharp enough to crack small seeds. Their jaws are strong enough to strip bark. Independence approaches gradually rather than suddenly. By 10 weeks, weaning is complete. The young are feeding themselves entirely. The mother becomes less tolerant of their presence, sometimes chasing them away when they approach too closely. The family bonds are loosening. The kits spend more time apart from each other, exploring different sections of their mother's territory. Then comes separation, usually around 11 or 12 weeks of age. The young begin looking for their own territories. Some travel only a few hundred feet, settling in areas adjacent to their mother's range. Others move farther, seeking vacant spaces in the forest. This is when first-year mortality becomes significant. Many fail to find adequate territories before winter. Others claim spaces but lack the experience to cache sufficient food. Predators take some. Starvation takes others. Studies suggest only 30 to 50% of juveniles survive their first year. Those who do survive emerge from winter as experienced squirrels, ready to breed the following spring. The mother, meanwhile, might already be pregnant again. Some females produce 2 litters per year, the second one arriving in midsummer. This second litter faces different challenges. They mature during a season of abundance, but must still establish territories and cache food before their first winter arrives. Their timeline is compressed compared to spring-born litters. Through all of this, the male parent remains absent. He provided genetic material during that brief breeding encounter, but contributes nothing to raising the young. His energy goes into maintaining his own territory and seeking additional breeding opportunities. This pattern is common in mammals. Males invest in mating. Females invest in offspring care. The strategy works because it maximizes each parent's reproductive success. The male can potentially father young with multiple females each year. The female can only raise 1 or 2 litters annually, regardless of how many males she mates with. Evolution has shaped their behaviors to match these different constraints and opportunities. And so the cycle continues, young squirrels born each spring and summer, some surviving to adulthood, others disappearing before their first birthday. The population maintains itself through this constant turnover, older individuals eventually dying and being replaced by the successful young who manage to claim territories and survive their first winter. But success requires more than just luck or determination. It requires information about predators approaching, information about food locations, information about territorial boundaries and social relationships, and gathering that information depends on senses that operate constantly, processing the forest environment and translating it into survival decisions made dozens of times each day. Chapter 10. Those young squirrels learning to navigate the canopy faced a world full of information. Every branch carried meaning. Every sound suggested danger or opportunity. Every scent told stories about who had passed this way and when. The forest spoke constantly in languages built from light and shadow, vibration and chemical traces. Understanding these languages meant survival. Watch a squirrel sitting motionless on a branch in the afternoon light. Its head is still, but the eyes are moving, scanning the space around it in patterns we can barely detect. The eyes sit on the sides of the head rather than facing forward like ours do. This placement gives the squirrel a different view of the world, one that stretches almost completely around its body without requiring any head movement. The visual field extends roughly 270 degrees, nearly a complete circle. Only a small blind spot exists directly behind the head. Everywhere else the squirrel sees without turning. A hawk approaching from the left is visible. A predator moving from the right registers immediately. Even motion slightly behind the squirrel enters peripheral vision, triggering awareness before danger arrives. This wide view comes at a cost. The images lack some of the sharpness that forward-facing eyes provide. There's no stereoscopic vision in most of the visual field, no overlapping images from two eyes creating depth perception. But for a prey animal, seeing everywhere matters more than seeing in precise detail. Better to notice movement in time to escape than to see that movement with perfect clarity a moment too late. Colors appear different to squirrels than to us. Where we see red leaves in autumn, squirrels see yellowish-green. The receptors in their eyes respond to blue and yellow wavelengths, but not to red. The forest canopy must look different through their vision, a world painted in fewer colors but no less rich for that limitation. Distance judgment happens through other cues. The squirrel moves its head side to side, watching how objects shift position relative to each other. Closer objects move more, distant objects move less. This parallax effect provides depth information that compensates for the lack of overlapping visual fields. Before a jump, the head movements become more pronounced, the squirrel gathering as much distance information as possible before committing to the leap. Light levels affect what squirrels can see. Bright daylight brings their vision to peak performance. The cone cells in their retinas respond to color and detail, processing the well-lit forest into clear images. But as evening approaches and shadows deepen, those cone cells become less effective. The rod cells, which detect light intensity without color, take over. Vision becomes monochrome and less detailed as darkness grows. Full night renders squirrels nearly blind compared to truly nocturnal animals. They have some night vision, enough to navigate familiar routes in dim moonlight, but nothing like the capabilities of owls or flying squirrels. This limitation shapes their daily schedule. Active during daylight, resting in the nest after dark. The pattern follows their visual abilities rather than fighting against them. Sound carries differently through the forest than light does. It bends around obstacles. It reflects off surfaces. A squirrel listening from one branch might hear events happening several trees away, sounds traveling through air and wood to reach ears that are constantly monitoring the environment. The hearing range extends beyond what human ears can detect. High-frequency sounds that we can't perceive register clearly to squirrels. This sensitivity matters for detecting alarm calls, the warning chirps that other squirrels make when predators approach. The calls carry information in their frequency and rhythm, telling listeners not just that danger exists, but what kind of danger and how urgent the threat might be. Squirrels also hear the sounds of approaching danger before visual detection becomes possible. A pine marten moving through branches creates small noises, claws scraping bark, leaves rustling, branchwood flexing under weight. Each sound provides information about distance and direction. The squirrel's ears rotate independently, orienting toward sound sources, triangulating the location of whatever is making noise. But hearing alone doesn't identify what approaches. Sound says something is moving. Vision confirms what that something is. The two senses work together, each filling gaps the other leaves. Hearing provides early warning. Vision provides identification. Together they create awareness that's greater than either sense alone could achieve. Scent adds another layer of information. The world carries chemical traces everywhere. Trees marked by other squirrels, predator odors lingering in areas where danger recently passed, food sources detectable from distances that sight and sound can't reach. The squirrel's nose processes these traces constantly, building a chemical map of the territory that updates with each breath. Finding cached food in winter depends heavily on scent. Memory brings the squirrel to the general area. Visual landmarks narrow the search to a specific zone. Then scent takes over for the final approach. Even through snow, even through frozen ground, molecules from buried nuts rise slowly upward. The concentration is faint but detectable at close range. The squirrel follows this chemical gradient downward until its digging reaches the cached item. Social information also travels through scent. A squirrel can tell whether another squirrel passed this way recently, whether that squirrel was male or female, whether it was familiar or unknown. All of this encoded in chemical signatures left on bark and branches. The scent marks serve as messages, information posted in public spaces for any squirrel with the ability to read them. Touch operates at the finest scale. Whiskers extend beyond the face and body, sensitive hairs that detect nearby objects without direct contact. When a squirrel investigates a narrow crevice or approaches an object in dim light, the whiskers arrive first. They brush against surfaces and bend, the deflection sending signals to the brain about texture and distance. The paws also gather tactile information constantly. Bark texture indicates which trees provide good grip. Branch thickness suggests how much weight it can support. Surface temperature tells whether the metal roof of a building is safe to walk on or dangerously hot. Every surface the squirrel touches provides data that refines understanding of the environment. all these senses operate simultaneously. Vision scans for movement. Hearing monitors for sounds. Scent detects chemicals. Touch feels surfaces. The brain integrates information from all sources into a unified awareness of what's happening around the squirrel at any given moment. Threats get detected through whichever sense notices them first. Then the other senses focus on gathering additional details. The system isn't perfect. Sensory information sometimes conflicts. A shadow moving might trigger alarm but turn out to be just leaves shifting in wind. A sound in the branches might seem like danger, but actually be another squirrel passing through neutral space. The squirrel must constantly evaluate which signals matter and which can be safely ignored. Experience improves this evaluation over time. Young squirrels freeze at every unexpected stimulus, their inexperience making them unable to distinguish real threats from false alarms. Adult squirrels show more discrimination. They've encountered thousands of situations and learned which patterns actually indicate danger. The freeze response becomes more selective, triggered by genuine threats rather than every anomaly. But even experienced squirrels make mistakes. A predator approaches using tactics the squirrel hasn't encountered before. The sensory warning comes too late or gets interpreted incorrectly. These failures cost lives. The squirrels who survive are those whose sensory processing was accurate, often enough to avoid the predators and accidents that remove less fortunate individuals from the population. The modern forest contains stimuli that didn't exist in the environment where squirrel senses evolved. Car sounds, human voices, artificial lights. Squirrels in urban settings must learn to filter these novel inputs, determining which ones matter for survival and which are just background noise. Most adapt successfully, their behavioral flexibility allowing them to function in environments that would have been incomprehensible to their ancestors. Yet the basic sensory abilities remain unchanged. The same eyes that watch for hawks in wilderness forests watch for hawks in city parks. The same ears that detect pine marten footsteps also hear dogs approaching on pathways. The same nose that finds cached acorns in the wild finds them in urban yards. The senses adapt to new contexts while maintaining their fundamental functions, and those functions continue serving the same ultimate purpose they've always served: detecting food, avoiding danger, navigating space, finding mates. Every sensory input contributes to decisions that affect survival and reproduction. The squirrel doesn't think about vision or hearing or scent as separate systems. It simply experiences the world as a unified whole, responding to what its senses tell it moment by moment through each day. Those responses happen in wild forests and in spaces humans have built. The squirrels who live near us face different challenges than their counterparts in untouched wilderness. They navigate between two worlds, adapting behaviors that evolved for forests to environments shaped by human presence. And in making that adaptation, they reveal something about their flexibility, their ability to persist in changing circumstances. Those senses that read the wild forest now read a different landscape. Trees still stand, but pathways run between them in straight lines. Buildings rise beyond the canopy. Sounds of traffic hum in the distance. The squirrels who live here navigate between worlds, 1 foot in the ancient patterns, 1 foot in spaces humans have shaped. Morning arrives in the city park much as it does in the forest. Light filters through branches. Birds begin calling. The air is cool and still. A red squirrel emerges from its nest high in an oak tree, pausing at the entrance to survey the space below. The same routine that plays out in wilderness forests plays out here too. Check for danger, check for changes, begin the day. But the space below looks different than wild ground. A paved pathway curves through the trees. Benches sit at intervals along the path. A trash bin stands near one bench, its metal surface catching early light. These human additions create a landscape the squirrel has learned to navigate, weaving between natural and artificial elements as if both have always existed together. The squirrel descends the oak trunk and moves along a low branch that extends over the pathway. It pauses there, watching. No people yet. Too early for the morning walkers who will arrive in an hour or two. The path sits empty in the dawn quiet. After a moment, the squirrel continues down to the ground and crosses the pavement in quick bounds, reaching another tree on the far side. This crossing happens multiple times each day. The pathway divides the park but doesn't stop the squirrel's movement. It's simply another feature of the territory, like a stream or a fallen log, something to cross when routes require it. The pavement feels different under the paws than soil or bark, smooth and unchanging, but the squirrel has walked it hundreds of times and knows its texture. Food sources in the park include natural items and human contributions. Acorns fall from the oaks in autumn just as they do in forests. Pine cones appear in the conifers. Seeds scatter from various trees through the growing season. But people also leave things: breadcrumbs on benches, peanuts scattered intentionally by park visitors who enjoy feeding squirrels, dropped snacks that get forgotten. The squirrel has learned which of these human foods are worth eating and which should be avoided. Bread provides some nutrition but less than natural seeds. Peanuts are acceptable, though not preferred over the hazelnuts that grow on bushes near the park edge. Processed foods with strong artificial smells get investigated but usually ignored after the first taste proves uninteresting. One woman arrives each morning around 8 o'clock. She walks slowly along the path, carrying a small bag. When she reaches a particular bench, she sits and opens the bag. Hazelnuts. She places them on the bench beside her and waits. The squirrel knows this routine. It approaches cautiously even after months of repetition and takes a nut from the bench while the woman sits motionless. Then it carries the nut away to eat or cache, depending on the season and its hunger. This interaction happens in silence. The woman doesn't speak, the squirrel doesn't vocalize. There's an understanding between them built through daily repetition rather than communication. She provides food, the squirrel accepts it. Both seem content with the arrangement. After taking several nuts, the squirrel departs and the woman continues her walk through the park. Territory size in urban parks tends to be smaller than in forests. Food concentrates in smaller areas. The woman with hazelnuts represents a reliable source that requires little energy to exploit. Other park visitors provide additional opportunities. Trees still produce natural food. The combination means adequate nutrition can be gathered from a more compact space. The squirrel's home range here spans perhaps 1 acre, maybe less. It knows every tree intimately, which branches provide the best routes, where the most productive feeding spots are located, which areas see heavy human traffic, and which stay quiet through most of the day. The mental map is detailed and constantly updated based on seasonal changes and daily observations. Other squirrels occupy adjacent spaces in the park. Boundaries exist here as they do in forests, though sometimes the territories overlap more than they would in wilderness. Food abundance allows some flexibility. The territories are defended, but not with quite the same intensity that accompanies midden protection in wild populations. There's less to lose when food remains available year-round through human contributions. Interactions with people vary widely. Some visitors ignore the squirrels completely, walking past without acknowledgement. Others stop and stare, pointing, sometimes attempting to approach. Children often run towards squirrels, their enthusiasm triggering immediate flight responses. The squirrel has learned to maintain distance from fast-moving humans, especially small ones whose behavior is less predictable than adults. Dogs present a more serious concern. They appear regularly in the park, walking on leashes beside their owners. Most dogs show interest in squirrels, pulling toward them, sometimes barking. The squirrel's response is always the same: immediate retreat to the nearest tree. Rapid ascent to heights dogs cannot reach. Wait there until the dog passes, then descend and resume normal activity. These encounters happen multiple times each day during busy periods. They're disruptive but manageable. The squirrel loses a few minutes of foraging time, but nothing more serious. It's learned that leashed dogs can't pursue effectively. The threat is more annoyance than genuine danger. Unleashed dogs would be different, but park rules require leashes and most people follow them. Seasons change in the park as they do everywhere. Autumn brings falling leaves and cooling temperatures. Winter brings snow that covers the ground and rests in branches. Spring brings new growth and longer days. Summer brings heat and the full green canopy. The squirrel's behavior shifts with these changes, following patterns embedded deep in its biology. But the shifts are softer here than in wild spaces. Food never disappears entirely. Even in winter, the woman still comes with hazelnuts. Other visitors still scatter peanuts. The trash bins still overflow after weekend crowds. The urgency that drives wild squirrels to cache thousands of cones doesn't apply as strongly here. Some caching still happens, the behavior too fundamental to abandon completely, but the amounts are smaller and the desperation is absent. The squirrel still builds nests, still maintains them through the year, still raises young in spring. The fundamental life cycle continues unchanged, but it unfolds against a backdrop of human presence that wild squirrels never experience. The sounds of traffic become background noise, noticed only when unusually loud. Human voices blend into the park's soundscape. The squirrel learns to distinguish between people who might provide food and people who pose no interest either way. Years pass this way. Seasons cycle through their familiar patterns. The squirrel ages gradually, its movements slowing slightly, its reflexes becoming fractionally less sharp. Young squirrels appear each spring, some staying to claim territories in the park, others dispersing to find spaces elsewhere. The population maintains itself through this turnover, older individuals eventually disappearing and new ones taking their places. One morning, the squirrel doesn't emerge from its nest at the usual time. Inside the dray, curled in its sleeping position, it has simply stopped. No struggle, no apparent distress, just the quiet ending that comes to all living things eventually. The nest will sit empty now until another squirrel discovers it and claims the structure for its own use, but that morning is still far off. For now, the squirrel continues its daily routine, emerging at dawn, checking the territory, finding food, watching for danger, resting in afternoon shade, returning to the nest as evening approaches. The rhythm is ancient. Older than parks, older than cities, older than human civilization. It continues because it works, because generation after generation of squirrels have followed these patterns and survived long enough to pass them forward. The park around the squirrel changes slowly. Trees grow larger, old trees fall and young ones take their places. The human city beyond the park boundaries expands and contracts with economic cycles. New buildings appear, old ones are demolished. Through all of this, the squirrels persist. They adapt to changes when necessary. They maintain traditions when possible. They exist in the spaces between wild and tame, belonging fully to neither category, but succeeding in both. The squirrel's breathing slows. The day's memories, if we can call them that, fade into whatever passes for sleep in a squirrel's mind. Tomorrow will bring another dawn, another emergence from the nest, another day of navigating between worlds. But that is tomorrow. Tonight, there is only rest, safe and warm, high in the branches above the quiet park.